Hi, I'm Nick Moffett with Verisurf Software. In this video, I'll show you how to use the CMM Master with Verisurf Metrology software to automate part inspection on the shop floor in order to reduce scrap and increase productivity. You'll see how to create inspection plans using Verisurf Automate and then run them in AutoInspect. You'll also see how to create plans using Teach Mode and how to use the CMM Master as a comparator. The system is based on the proven Renishaw equator and enhanced using Verisurf's cubic volumetric mapping. The result is an accurate CMM that provides fast, affordable in-process inspection. The CMM Master is designed for use in a shop environment. It draws less than 200 watts, doesn't require an air supply, and operates over a wide temperature range. The machine weighs only 55 pounds and is roughly a 2-foot cube, so it's very portable. The volumetric accuracy is plus or minus 5/10,000ths of an inch, and the working volume is a cylinder with a 12-inch diameter and a 6-inch height. In addition, an extended height model is available for measuring taller parts. It supports the Renishaw 3-axis SP25 scanning probe kit and scans at a rate of 1,000 points per second. In addition, each CMM includes a certificate of calibration and a 12-month warranty. Finally, the CMM Master is supported by a wide variety of standard and optional probe and fixture accessories. Standard accessories include a 6-position probe rack, fixture plate, joystick, SP25 probe, and cleaning kit. Optional accessories include basic, intermediate, and advanced kits with 15, 22, and 33 probes respectively. 2 enclosure options are available, and the fixture accessories include plates and modular kits that provide maximum flexibility for mounting parts. We've seen an overview of the hardware. Next, we'll see how Verisurf supports open standards and modular software. Verisurf is committed to open standards that simplify manufacturing measurement solutions by providing our customers the freedom to choose the hardware that's right for them. Open Device Connection allows Verisurf to drive virtually all portable measuring devices, including portable arms, laser trackers, scanners, and fixed CMMs, making Verisurf a common metrology platform. Open CAD compatibility ensures that Verisurf will work with all popular CAD formats, including IGES, STEP, Pro-E, SolidWorks, NX, CATIA, and numerous others. Open CMM Communications extends our open standard support to all CMMs committed to the I++ DME protocol. Finally, the Open CMM curriculum from Verisurf University delivers online learning, customized on-site training, and lab and classroom support for educational institutions. Verisurf's modular software design allows you to select the functionality that's right for your application and budget. We've already seen how Automate enables CMM programming and operation. Verisurf CAD implements OpenCAD compatibility and is the foundation for all other modules. The Measure module enables inspection and reporting of prismatic features, and Analysis performs point cloud to model, best fitting, and comparison. The Build and Project modules enable guided positioning of objects to their nominal orientation, and Reverse creates mesh, surface, and solid models from point clouds. Finally, Validate helps to ensure that your nominal data matches the digital authority. We've seen the benefits of open standards and modular software. Next, we'll see how cubic volumetric mapping improves the accuracy of the CMM Master. The feature that differentiates the CMM Master from a standard Renishaw equator is the application of Verisurf's cubic volumetric mapping. Verisurf starts by using a laser interferometer to map the position errors throughout the equator's measuring volume. We then apply a 24-parameter correction model to compensate part measurements in real time. The result is a CMM that's not only repeatable, it's accurate as well. Every CMM Master comes with a calibration certificate, and because the cubic volumetric mapping is done through software, the manufacturer's warranty remains valid. If you already own an equator and would like to take advantage of cubic volumetric mapping for increased inspection accuracy, Verisurf will error map your machine for a minimal fee. The CMM Master is powered by Verisurf Automate, a graphical object-oriented programming language that works inside Verisurf's 3D CAD environment. The intuitive interface allows even novice users to program part inspections. I'll start by loading a model of the part that we want to inspect. Then I'll hide the device and zoom in for a better view. For this example, I'll create a simple inspection plan to measure and analyze the hole pattern, the slot, the sphere, and the cone, and I'll measure the edge lines to check parallelism and perpendicularity. I'll also inspect surface profile on the front of the part. It's a simple plan, but it demonstrates many of the features of model-based programming. To begin, I'll select the Automate tab and create a new plan. Next, I'll add circles for the hole pattern, the large ID hole, and the boss by selecting the features in the model that define their nominal values. We can see these values in the grid view as we highlight each circle. I'll continue by adding the slot, the sphere, and the cone using the same method. Finally, I'll add the 3 lines on the top edges. Once the features have been added to the plan, we generate a drive path for them. I'll highlight circles 1 through 8 and choose Generate Path. In the Generate Path dialog, I'll then configure the path to measure 8 points on the inside of the holes at a depth of 1/10 of an inch. On the CMM Settings tab, I'll use the top WCS to control the entry and exit vectors and set their distance to 1/2 inch. The WCS is a powerful programming tool that allows us to align the entry and exit vectors to a reference plane if necessary. Using the WCS control, we can orient these vectors to any of the standard or even custom WCS views, regardless of the feature vector. Notice that I can adjust values such as entry and exit vectors, approach and retract distances, and many other settings simply by scrolling the mouse wheel, and the effect on the path is visible in real time. This works for all of the scroll controls. I'll complete the path for the small holes by enabling scanning at a spacing of 80,000ths of an inch. We can scan any feature on the part simply by choosing Enable Scanning. When I generate the path for the large hole, I'll increase the number of points to 10 using the same depth as the small holes. On the CMM Settings tab, I'll set the clearance vector to top and adjust the entry and exit distances. To measure the boss, I'll move the path to the outside of the circle and then reduce the number of measured points to 4. Notice that the path nearly intersects the surface. I'll compensate by adding a clearance point between each measurement. I'll also set the approach and retract distances to 150 thousandths and adjust the entry and exit vectors. Next, I'll configure the slot to measure 5 points at a depth of 1/10 of an inch, and then adjust the entry and exit vectors. For the sphere, I'll use 20 points on the inside spread over 3 rows, and I'll reduce the coverage to 90% to avoid measuring too close to the rim. I'll also adjust the entry and exit vectors and enable scanning. For the cone, I'll configure the path to measure 10 points on each of 3 rows with 150 thousandths separation. I'll then adjust the entry-exit as I did for the sphere and enable scanning. Finally, I'll create paths for the 3 lines. I'll start by moving the ends in 1/2 inch from the tangent points and clamps, and then lower the depth. I'll also adjust the clearance vectors to avoid the fixture clamps, and then enable scanning. To inspect surface profile, I'll add a surface grid to the plan. In the Generate Path dialog, I'll select the front surface and then use the UV control to create a 16 by 2 grid. The shift, offset, and rotation controls allow us to conform the grid to virtually any surface. We can see in real time how the changes to these values affect the path. Finally, I'll enable scanning for the profile measurement using a 1/2 inch spacing. When we run the plan, Verisurf will measure and report surface deviation at each point in the grid. The plan is now essentially complete, so we can run the simulator and observe the path. The simulation controls allow us to start, stop, and vary the playback speed. We can also highlight a single feature and simply drag the slider for greater control. Features can be positioned anywhere in a plan using drag and drop or cut and paste. Notice that I can improve the efficiency simply by moving the lines to the top, followed by the sphere and the cone. I'll do this by highlighting and then dragging the groups of features. The purpose of the inspection is to report results, so I'll complete the plan by adding callouts to report parallelism and perpendicularity between the lines. I'll highlight lines 1 and 2 and choose perpendicularity, and then do the same for lines 2 and 3. I'll then highlight lines 1 and 3 and choose parallelism. I'll also construct a circle through the hole pattern. I'll highlight circles 1 through 8 and then choose Construct Circle. In the Details pane, I can use the checkboxes to select the maximum angle and spacing for the report. I'll use the Report button on the toolbar to open the plan in the Report Manager, where we can see the features and calculations with various properties selected for reporting. Next, I'll clear the report and then select the PDF format for file output. Before saving the file, notice that I can restrict access to Automate and the Report Manager to prevent accidental or intentional modification of the inspection plan. The plan is now ready to run. In the following steps, we'll align the device and then inspect the part. Before running the inspection, we need to align the CMM master to the part. I'll do this using AutoAlign since it's the easiest way to align using a CAD model. In the Measure Manager, I'll choose Create Target and then click on the model to create the alignment target locations. Since the model includes datum targets, I'll place the alignment targets at the datum target locations. When I'm done, I'll save the file and then choose Run Auto Align to begin the alignment. As each target is highlighted, I'll use the joystick to drive to and then measure the alignment point. As we'll see later, the joystick can be used for manual measurements as well as teach-in mode. When the final target is measured, Verisurf aligns the device using a best fit and then displays the results. Since the results look good, I'll choose to accept. The CMM master is now aligned to the part, so we're ready to run the inspection. Inspections are run in Verisurf using AutoInspect. This interface can be used with a manual or automatic device to measure a part. It can also be used in offline mode to analyze existing data. When I open AutoInspect, we see the list of features, the surface grid, and the calculations that make up the plan. I'll configure AutoInspect to display a report as soon as the inspection is complete. Next, I'll choose Run and verify that the CMM is ready. As the plan executes, the maximum deviation of the selected properties for each feature is displayed. If all the selected properties for a feature are in tolerance, it's highlighted in green, otherwise it's shown in red. Notice that while the inspection is running, I can switch to another instance of Verisurf to continue programming another inspection. This makes the system very efficient. When the inspection is complete, Verisurf opens the report to display the results. In it, we see the feature properties that we chose to report. To demonstrate offline inspection, I'll clear the results and then export the analysis to a point cloud. When I choose Run Offline, Verisurf recalculates the results and displays the data from the initial inspection. Next, I'll place another part in the fixture and rerun the inspection. Rather than align the part using the joystick, I'll add Auto Align to the inspection plan so we can run it automatically. I'll highlight the targets and add them to the plan. In the Automate Manager, I'll move Auto Align to the top of the list. Notice how we see the change reflected instantly in the Auto Inspect dialog. I'll then clear and run the plan, which now begins with the alignment. When the plan is complete, Verisurf displays the inspection report. We've now seen how to program an inspection and check multiple parts using automation. Next, we'll see how to measure in manual mode and how to use Teach mode to program an inspection. In manual mode, we measure by using the joystick to drive the probe. As we'll see, this is another way to program an inspection. Although we're using a model for this example, manual measurement is also a convenient way to program an inspection in a print-based workflow. I've opened a new file and aligned to the model, so I'm ready to begin measuring features, and I'll start by measuring a plane on the top of the part. Next, I'll measure 4 of the holes in the pattern. I'll measure the 2 end planes so that we can check parallelism. Finally, I'll select Inspect Build Mode and check Profile at a few locations along the front of the part. When the measurements are complete, I'll create a report to analyze and display the results. When I do, Verisurf adds the report as a plan in the Automate Manager. In Verisurf, plans and reports are synonymous. When we create a plan, it also creates a report to analyze and display the results of the plan. And when we create a report, it also creates a plan to measure the features in the report. In this respect, Teach mode in Verisurf is as simple as measuring a part and creating a report. With the Report Manager still open, I'll construct a circle through the hole pattern. I'll also create a parallelism callout between the 2 planes. Looking at the plan in Automate, we can see the calculations as I add them to the report. In Auto Inspect, I'll clear the results and then run the plan. When the inspection is complete, Verisurf displays the report. We've now seen how to automate an inspection using both Automate and Teach mode. Next, we'll see how to use the CMM Master as a comparator. In our previous examples, we've analyzed measured features and surface profile to nominal values. In some cases, however, we want to compare a batch of parts to the initial measurements of a reference or golden part. We refer to this application as comparator mode. To save time, I've loaded a model that has an alignment and a surface inspection programmed, and the part is already aligned. I'll start by measuring the golden part. When I run the plan called inspection, we'll see the deviations of the golden part from the nominal model. These are the deviations to which we'll compare subsequent parts. If I were to rerun the inspection plan, we'd see the same deviations from nominal as the initial run. Instead, I'll create a new plan from the initial inspection and rename it Comparison. I'll then change the measure settings to show repeatability from the original measurements of the golden part. If I clear and then run the plan called Comparison on the golden part, we'll see 0 deviations because we're comparing the golden part to itself. I'll replace the golden part with a similar check part and then rerun the comparison. The check part is now fixtured, so I'll start by running auto align. When the alignment is complete, I'll clear and then run comparison on the check part. This time, we see deviations that represent a comparison of the check part to the golden part. The use of the CMM Master as a comparator increases inspection flexibility by replacing single-purpose hard gauges. It simplifies inspection where measured rather than nominal data is the basis of comparison. That concludes the presentation. I hope I've given you a good appreciation for how Verisurf and the CMM Master can help expand your inspection capabilities, increase inspection throughput, and reduce your overall QA costs. To learn more about the benefits of inspection automation and the CMM Master, please call us at 888-713-7201 or email us at sales@verisurf.com.